Hello, my name is Ashok, and I'm presenting this work. It's modeling equilibria under rationality. It's joint work with Helen Lukat and Anna Bushish, and is here. So this is based on our preprint, which is available online. Um, Generally in game theory, we assume that rationality is a given thing, that it's true that everyone is rational. However, humans are known to be not fully rational, so this is something that needs to be incorporated in game theory. And for this work, we use some ideas from prospect theory, which is something that is there from the literature of economics and decision theory, in order to model some aspects of irrationality in game theory. So in outline of the talk, I will be presenting the game model, and then I will just try to explain what's there in the model and try to show the equilibria, which is Nash equilibria. And then I will try to make the players slightly irrational by using prospect theory. And then the game model becomes slightly different. So we'll be working with the example of an electricity market. And this is our main area of interest because, well, our funding is from EDF. So imagine you are a customer for an electricity market, and the game is structured that the customers, before they begin the consumption, they kind of have to predict how much they're going to consume. So it's like you have a plan about how much you're going to consume, and you inform the consumption, the electricity company about how much you're going to consume. So let's call this Y. So each person has a yi, which is some block, the amount that they're going to consume, y1 to y5 here. However, in practice, so this basically, for the electricity company, this is a good thing because with this y's, they can make a target y, which they can use to produce electricity. However, you end up consuming some other quantity x, which is maybe higher or lower than y. So then, there is the difference between these quantities. And the game is basically modeled to kind of match it somehow, but also in two ways. So basically, I'll explain. So there are two quantities here, but one is the summation of your plan and what you actually consume, which is summation of xi. And the other quantity is basically your own personal. So if you look at user 4, they planned y4, but they consumed x4. So this quantity, the joint, is like a social or collective, it's a collective term that is applied to all the users. And the second is like a personal cost. So for this game, we have the utility. It's like an equation where the first term basically models the collective effect or the aggregative across all users. The second is the cost based on a price. P is the price that the users pay for every unit of consumption. And finally, they also pay an excess charge for not meeting the target. And this not meeting the target quantity runs with a random variable psi because the price that you pay for not meeting your plan is basically random because it depends, because from time to time, the electricity company has this production cost, which itself is random. For example, it can be based on the cost of renewables and so on. So once you define a game like this is a very simple and standard game, convex game. You can define equilibrium. I will not define what it is, but it is possible. And generally in game theory, you are concerned with the existence, uniqueness of the equilibrium and whether you can reach this equilibrium by some kind of algorithmic process. So in this case, you can show that equilibrium exists for such a game, and these equilibria are non-unique. And so you can actually plot the equilibrium. For example, for 3 users, the equilibrium kind of looks like this. It's like points on a triangle because the summation of xi have to be equal to a certain constraint. And this is These are non-unique, but once you have multiplicity of equilibria, there are questions like which equilibrium is to be selected and so on, but these can be addressed separately. Now, I'll skip that. Now, in order to make this game model a little irrational, what we do is we change the utility function slightly. We introduce a term, a transformation called V here, which transforms the utility. And this V is called a value function. And this value function is something that should look like this. This is a picture taken from this paper, which was the work that introduced prospect theory by Kahneman and Tversky. So what this function basically captures is that when people are looking at some kind of utility, their perception of the utility depends on whether they perceive themselves as being in a system of gain or in a system of loss. So if you're in a system of gain, you tend to look at it in a certain way, which is the concave function on the right. And if you're in a regime of loss, you kind of look at the utility in a certain other way. So, I mean, this is one aspect of decision making under risk that is captured by such functions. So once you have this kind of a function, of course, we cannot work with all kinds of V's because we are limited by the amount of mathematics we can do. So we will assume for this talk that V's are monotone, concave, and differentiable. These are not capturing all kinds of value functions in prospect theory, but they do capture an interesting subclass, which are at least on one side, they are on the positive side of gains, they are risk averse, and on the negative side of losses, they are risk neutral, for example. What we show is that for such classes, equilibrium exists. This is rather straightforward, but these equilibria, again, are not necessarily unique. What we also see, for example, is how the equilibria are transformed as you change the number of players who are irrational. So this is one example. So these are the original rational equilibria. And while you may not expect them to survive under the transformation, actually some of them do. What happens is, for example, we have three players here, x1, x2, x3. And as we make player x1 irrational, the number of equilibria, well, it changes from the plane to the green line. And when I make x2 irrational as well, now the number of the equilibria basically shift to the intersection of the two lines, which is exactly 1 point. So by just increasing the number of irrational players, we can kind of reduce the number of equilibria. But these are the rational equilibria that we had in the beginning. And it is very much possible that the transformation may introduce its own new equilibria. And well, for that, okay. And in fact, some of the old equilibria. In this case, for example, when the three users become irrational, none of the previous equilibria are preserved. So it might be that you get none of the old equilibria, but perhaps there are no new equilibria as well. So we have some results in this regard, which I will skip for now. But I will just give some examples in terms of value functions and the kind of equilibria that are generated. A simple function is the exponential function, which is not traditionally a prospect theoretic function, but it is close enough. And in this case, if all the users are transformed, then you would actually get unique Nash equilibrium. Unique Nash equilibria are interesting because it becomes easier to design learning algorithms to go to this point. If you have multiple equilibria, then it's kind of difficult. You have to first choose which point to go to and becomes a bit arbitrary. But in this case, for example, you have unique equilibria. And the equilibria also satisfy a nice structural constraint. So it basically means that the excess consumption of each user, they have to be equal. So irrationality kind of forces this nice symmetric property onto all the users, even though in the rational case, that was not necessary. And these are just equilibria parameterized by price for a two-player case. And as we increase the price from 1 to 50, which was a parameter P, the equilibria just slides down. And they're all on this line because the line represents this constraint, this structural constraint that I've shown here. And in this case, yeah, so these are numerically obtained, not theoretical equilibria, because it's still not easy to characterize theoretically what the equilibria will be. I mean, you can solve them numerically by solving a fixed point equation. And another prospect theoretic function that we use is the linear and logarithmic function. So it's log on the right and linear on the left. And in this case, we observe that there are multiple equilibria, but these are possibly finite. So yeah, these are some of the equilibria we obtain. And you can see that there is a general trend along the positive slope line, which is the kind of the trend that we observed in the exponential case. But there are also outliers. And well, we are still working on how to better understand the cause for some of these outliers. But the central dotted line, which is the negative slope line, is basically some of the old equilibria from the rational case that survive in the irrational case. So yes, so this there are many more things that we're investigating, further conditions on the existence and uniqueness, and some further ideas on how to learn equilibria and how can we understand more if there are multiple equilibria, which ones are kind of stable, which ones are learnable, and so on. So that's it. Thank you very much.
Any questions? Thank you for the talk. Two questions. The first is a clarification. What information do the users have? Do they know X and Y, or?
So for learning, you would require the summation of X and the summation of Y. But you don't need to know
No, the players, I mean.
Yeah, the players need to know the summation of X and the summation of Y.
But they know XI and YI their own?
No. I mean, yes, right now they do need to go on the curve. Yes, you do need.
Okay, because then the second question, if they do they have the ability to affect? So if they have advertised XI, can they affect YI? I mean, so if I just think in the context of an energy market, right, where typically you say I subscribe to that many kilowatts, and if you exceed, then you're being hit with a very high penalty. And so you have incentives to modify your behavior.
Yes.
To adapt when you get close to this particular maximum so that you can avoid the penalty. I was just curious in terms of
So,
whether or not that's accounted for, or is that part of things that you're going to be looking at?
What I've not mentioned in the model, there is a price which is set by, so we have a coordinator which sets a price and which controls. So I've skipped that whole scheme because it just makes it very complicated to describe, but it's there in the paper, which basically the coordinator can move the users to a certain behavior using this price as a kind of incentive. So it's possible.
Okay. So that's embedded in the result of the equilibria here?
Yes, because these are parameterized by this price. So the numbers beside the equilibria are actually the price that are being set. So that parameter basically lets you move. As you can see, you go from 1 to 65 and you move in a certain direction. Here it's a bit rough because it just moves a little up and down, but it's possible that you can kind of isolate some structure out of it.
Okay. So, but that I guess that confused me is that the figures that doesn't show what YI is, or Y1 and what.
So Y1 is 7 and Y2 is 4. Sorry, it's just
so that was the thing. Can the users then adapt Y1 and Y2?
Possibly. This is just a single shot game. So yes.
There's what?
A single shot game. So just doing a single shot.
Okay.
Yes, we are not even because we just wanted to identify the equilibrium.
Okay. All right. Okay. Thanks.
Thanks.
And welcome the last speaker.